Hello everyone, welcome back in the course of higher surveying, and we are in module 7, LIDAR grammetry. In the last lecture of this module, we have learned what is a laser and how laser can be used in order to collect the topographic information. And then we have seen two forms. One is the wave and another is the pulse. Wave is the continuous emission of the photons, like a continuous turning on of a torch. Secondly, the pulse is collection of photons over a short duration, and that is why when pulse is triggered, we have some number of photons which are compressed or which are sent over a very short duration. And as a result, we can compare this phenomena by turning off the torch and turning on the torch. So during the turn on time, we have thrown some number of photons in very short duration, and that is what we call the pulse. Based on the pulse, we have defined time of flight principle, where pulse will be triggered from transmitter and it will travel through the space, it will interact with the object surface and it will be reflected by the object. The reflected pulse will be again received at the receiver, and the time between the triggering and the receiving is called the time of flight. By measuring the time of flight, we can measure the distance between transmitter-receiver assembly and the object surface. This was the time of flight principle. On the other hand, we have the phase-based principle that we employ with the waves. In case of phase-based principle, we measure the phase difference of the triggered wave and the received wave. Moreover, in case of pulse, photons are triggered in very short duration, and because of that we have very peak energy or peak power of some photons, and because of that a pulse can travel for a long distance because it has high peak power. At the same time, wave, each and every photon of which has small energy, and that is why although the phase-based measurement is more accurate, but the photons of the wave cannot travel for a long distance. And as a result, we will use the wave for shorter distances and we will use pulse for longer distances. That means we will use the pulse for the topographic mapping if the distance is in order of 500 meter, 700 meter or maybe 1000 meter or more. So that was the idea we have developed in the last lecture. Then we have seen that if a pulse or a wave is triggered, how to measure the power or the energy of the reflected pulse or reflected wave. If the reflected pulse energy or power is less than certain threshold, we will ignore it, or if it is above a certain threshold, we will say that we have received the reflected pulse from an object surface. So by measuring the power of the reflected pulse, we will say, yes, first of all we have received the reflected pulse, and then we will say that what is the time difference between the triggered and the reflected pulse. So using the time of flight, we will find out the distance. So let us learn that how to acquire the data of the topographic surface using LIDAR. So in this lecture, we are going to discuss about the LIDAR data acquisition using pulse. So this lecture is lecture 2, LIDAR data acquisition. The book is still same. I would like to specify that we are first going for the airborne LIDAR data acquisition. This is a typical example of airborne LIDAR data acquisition. You can see here that there is an aircraft, and aircraft is mounted with 3 sensors. One is GPS, another is inertial measurement unit or IMU, and third is the laser scanner which is sitting at the bottom of the aircraft. We made the dot. There is a base station on the ground surface of GPS, and using the principle of differential GPS, I am calculating the position of the aircraft trajectory using GPS rover mounted on the aircraft. So we are showing here some GPS satellites to indicate the differential GPS positioning. Secondly, IMU, inertial measurement unit, it is measuring the attitude angle, the roll, pitch and yaw of the aircraft motion. We have the laser scanner. It is triggering the laser pulses using time of flight principle, and for each pulse it is measuring the distance between the laser scanner and the ground surface. We can see here that there is jet shape pattern or sawtooth pattern of data acquisition. On the ground surface. So, it is like sawtooth, or we also call jet shaped pattern or zigzag pattern. So, all three names are indicating this pattern of the data acquisition. So, this is the flight altitude of aircraft, which is shown by the arrow here. This is the swath, which is the width of the data acquisition across the flight line. So, this is the flight direction here, or direction of flight line. This 1.5 meter here, it is showing you the spacing of the two data points here and here. Then if I just take one particular line, for example this line from here to here, it is acquiring these many number of pulses, 1, 2, 3, 4 and 5. Each pulse is creating some footprint on the ground surface. So, that is creating the horizontal inaccuracy or horizontal uncertainty of the each pulse data of LiDAR. And this is the spacing 1.5 meter, which is in between the 2 points in a line. See, there are so many lines here. In each line we have, let us say, 5 number of points or 5 number of laser pulses hitting the ground surface, and they are reflected back by the ground surface. We are recording the coordinates of each and every pulse point. So, these are indicating the elevation of a point with respect to some datum surface. So, let us say Z1, Z2, this is Z3, Z4 and Z5 here. These boxes from here to here are indicating the uncertainty in the Z value of the topography or the point on the ground surface. So, this is a typical example of an airborne LiDAR data acquisition. So, what are the ideal conditions here? The ideal conditions are that there should not be any change of the altitude or the flying height. That means an aircraft should always fly at a constant height with respect to the ground surface. Further, there should not be any change in the attitude, which means aircraft should not vibrate like this. So, there will not be any change in the attitude or the roll, pitch and yaw values of the aircraft. The third thing is we should not change the speed. That means aircraft is moving at certain speed. Let us say the speed is v. So, we should maintain the speed v only. There should not be any change in direction of flying, which means if aircraft is flying in certain direction with respect to north, it should always fly in that direction only. And we will see in coming slides why do we expect these kind of ideal conditions. There are few elements in this airborne LiDAR data acquisition. The first is the aircraft and the flying crew. So, flying crew is ensuring smooth flying operations and desired quality of the data should be obtained, and that is why they ensure that there should be a smooth operations of the flying. Then we have sensors, we have DGPS, we have IMU and we have a laser scanner. So, these are also the participating elements of airborne LiDAR data acquisition. Third thing is the user requirements. For example, if you are a user of the LiDAR data and you have hired some agency to acquire the airborne data, you will definitely ask for certain quality of the data, and those qualities are called the user requirements. At the same time, there are some mapping agencies, for example, Survey of India or United States Geological Survey in USA. So, such agencies also demand some requirements or they also imposes some conditions, so that client as well as the data acquisition party both will be having standard operational procedures, and by following those standard operational procedures they will be acquiring the data of certain quality. So, both parties should fulfill those things, and that is why we call them mapping requirements. So, what are the roles of these elements and how to ensure quality of the data? Let us look into the first element, that is instrument or the sensors. The sensors are IMU, GPS and laser scanner. Laser scanner is the first and fundamental instrument that is firing the laser pulses towards the ground surface. So, what are the characteristics of a laser scanner? In the laser scanner, there is a laser gun and it is continuously firing laser pulses. So, laser pulses are continuously interacting with the mirror, which is shown here. This mirror is oscillating like this. This is a laser gun. So laser pulses are coming this way, and this mirror, it is diverting the laser pulses towards the ground surface. And as a result, if it oscillates like this, it will be diverting the laser pulses in multiple directions. And because of that, I will have some series of points on the ground surface in one line. As we have already shown that there are 5 points, and these 5 points are available because of the motion of the mirror. So this is a reflecting mirror, and now we can see in animation how does it work. So there is a ground surface, and there is a laser gun. Laser gun is firing the pulses, and now I am showing oscillation of the mirror like this. So it is continuously oscillating. Laser gun is also firing the laser pulses continuously. We have so continuous series of laser pulses fired towards the topographic surface. So these pulses are fired from the laser scanner towards the ground surface, and as a result we get so many number of pulses on the ground surface, and once the ground surface reflects those pulses towards the scanner, the receiver receives those responses and to record them. So what are the characteristics of the laser scanner? First of all, there are some n number of pulses that can be fired by the laser scanner in 1 second. So n number of pulses, those are fired in 1 second. We call it point repetition rate or point repetition frequency. PRF is more popular name for this capital N. Further, in this module, we are going to indicate PRF by F symbol. F is equal to N here. Then we have scanning frequency. As we know that F number of pulses are fired in 1 second by an oscillating mirror and laser gun combination. What does it do basically? Because number of pulses are very high, maybe 1 lakh or maybe 70,000 or 30,000, something in this number. So what mirror does? Mirror is oscillating and it is diverting the pulses towards the ground surface. If I fire 1 lakh number of pulses in 1 second, and this will be diverted with the help of scanner, so there is a role of this motion, and whatever number of cycles this scanner completes in 1 second, we call it the scanning frequency of the laser scanner, and we indicate it by the small f. And because of the small f, we have certain number of lines. In general, like the laser scanner always oscillates in one line only. So if aircraft is stable or hovering at one point like a drone, it will be creating only one line. However, because of the motion or the speed of the aircraft, it creates zigzag kind of motion like this. And this is the flight line. So I am showing now one line from here to here, and that is one scan line. It is one complete oscillation of one mirror from this point to this point. Let us say 1, 2, 3, 4 and 5. So I have f is equal to 5 hertz because 5 times mirror has oscillated, and as a result we got 5 number of lines of the data. So each line contains some data like this. So now these data points are indicating the topographic information. What is the field of view? So it is the maximum angle, this angle across which all laser pulses are fired, and that is what we call FOV, and we indicate by, let's say, 2 alpha. So with respect to the vertical line, we have this is 1 alpha and this is another alpha. So the 2 alpha is FOV of the scanner. What is the relationship between FOV and the scanning frequency f? Now you can see here, if this is FOV, and in the FOV a mirror is oscillating like this to divert the pulses. If this FOV is larger, mirror has to travel more distance. We have some limited power in the instrument, and if FOV is higher or FOV is larger, and so the mirror is traveling for more angular distance, and as a result I will not have higher number of scanning frequency. That means if a mirror has to travel for long distance, it will travel for less number of times. That means scanning frequency will be less, and as a result the scanning frequency and the FOV are inversely proportional. I can also write FOV into f is equal to a constant. So generally a laser scanner has this kind of characteristics, and that is an additional characteristics that we should always consider when we go for the airborne LiDAR data acquisition. Laser scanner has some more properties. The scanning pattern, we have just talked about the one zigzag pattern or the sawtooth pattern or the Z-shaped pattern. It can also create some kind of sinusoidal pattern or parallel pattern. We will see these patterns in the coming slides. Now we have point repetition frequency of the laser scanner. So point repetition frequency is generally in the order of 30,000 to 150,000 hertz, or so many pulses in 1 second. Flying height, so flying height is indicated by h. It is in the order of, let us say, 300 meter to 3500, but this flying height is regulated by some mapping agencies as well as civil aviation authorities. So we need to have special permission in order to fly at certain height. Now we have the swath. This length is swath. We have already indicated what is the swath, and we will go for the mathematical formulation in the coming slides. Each and every laser pulse has some beam divergence, and so it creates some horizontal accuracy or horizontal uncertainty. Then we have point spacing. We have two types of point spacing. One is along the flight line and one is across the flight line. Then we have physical limitation. That means FOV into scanning frequency equal to constant. So that is the physical limitation here. And then we have sequential firing. So that is another limitation we should always consider. What is the meaning of sequential firing and what is the impact of that? For example, if we fire 30,000 number of pulses, each pulse will go and interact with the object surface. It will come back, received at the receiver, and then after that only we will fire the next pulse. If we increase the flying height, each pulse will take more time to travel through the space, and automatically the number of pulses fired in 1 second or PRF will be less. There is one more reason for that, and that we have discussed in last lecture also. Each pulse should have more power in order to measure the large distance, so that once it travels through the space and comes back to the receiver, it will have enough energy that is reflected from the object surface. If I have a limited power, then I can fire limited number of pulses. So if I provide each pulse higher energy, so it can travel for a larger distance or larger flying height, automatically the number of pulses will be less if I increase the flying height. So now let us understand the scanning patterns that is created by the combination of the aircraft speed and the laser scanner movement. So the laser scanner is diverting the pulses or throwing the pulses across the direction of flight. So these three lines are indicating the flight directions. This is the first pattern where laser pulses are fired, and because of the aircraft speed, they are being collected in the Z-shaped or sawtooth pattern. So this is the sawtooth pattern or the Z-shaped pattern. So these are so many pulses fired in 1 second. What is scanning frequency? Let us say 1, then 2, 3, 4. So we have 1, 2, 3. So and it is showing 3.5. In fact, it does not happen. Generally, we have complete 4 cycles here. So let us draw few more points here. Scanning frequency f is equal to 4 hertz. Let us look into the parallel pattern. So parallel pattern is like that, where we create parallel lines. So now you can imagine that in case of Z-shaped pattern, if we remove these alternate lines, this line, this line, this line, and this line, I can create these parallel patterns. That means oscillating mirror is acquiring the data in only one turn, not in the return turn, and we can have the parallel pattern. Apart from that, we have one more pattern, sinusoidal pattern, where data is acquired in this fashion. As aircraft is moving and laser scanner is mounted over the aircraft, because of the movement of aircraft and laser scanning firing, we can create this kind of pattern. This is the sinusoidal pattern we have created here. So these three patterns are possible to create. There are some other patterns are possible. However, Z-shaped pattern is most dense data collecting pattern, and so it is most popular among all scanning patterns. And we are going to use this jet-shaped pattern only in this lecture. Let us understand the role of the DGPS and IMU. DGPS is Differential Global Positioning System. Aircraft has DGPS mounted over the top of that, so it is in connection with all satellites, and satellite lock is maintained. It is acquiring the data at every 1 second. So at every 1 second, it is acquiring X, Y, and Z position of the aircraft trajectory. During that 1 second, we are firing F number of pulses. During that 1 second in which we fire F number of pulses, IMU acquires roll, pitch, and yaw of the aircraft trajectory or the aircraft motion. Because of that, we come to know what is the motion of the scanner or how scanner is behaving. So then we can find out the trajectory of the aircraft between that 1 second also. And using that information, we can find out what is the coordinate for each pulse. And that is the role of IMU here. So these are the characteristics of the DGPS. It observes the 3D coordinates of aircraft trajectory, and it updates the data at every 1 second or 1 hertz. So the lock should be maintained. That means if aircraft is moving like that and it turns after some time back to the next line, lock should be maintained. Otherwise, if lock is lost, I will not get the GPS data. And that is the first condition we should consider when we integrate so many sensors and all the elements. Let us see the characteristics of the IMU. It observes the roll, pitch, and yaw with respect to true east, true north, and the gravity direction. Data rate is 60 Hz to 250 Hz. It depends like which quality of the IMU you are using. Now there is another problem with the IMU. It sleeps on the long flight lines. What's the meaning here? If we are carrying the IMU in an aircraft is continuously traveling in one line in one direction for more than 15 minutes, IMU will start accumulating the errors. And that is the problem with the IMU. And as a result, we should regularly turn the aircraft so that IMU should not sleep. Generally, we have aircraft speed in the range of 50 to 70 meters per second. Let us say it is moving at a speed of 50 meters per second for 15 minutes. So what is the distance here? 15,000 meters, which is 15 kilometers. So in general, flight line or one flight line, it is not so long of 15 kilometers. And as a result, we have to take a turn. And so this condition does not create much of the problem in the data acquisition. So nowadays, we are very much relaxed as far as IMU is concerned for the airborne data acquisition. Let us say that we have used IMU, we have used DGPS, and we find out the trajectory of aircraft. This is the ideal trajectory, and this is the flight line on the ground surface. Laser scanner, when mounted on an aircraft, it is acquiring the data at each and every fraction of second. So this is flying height. So now radar data is acquired by movement of the aircraft and operation of the laser scanner. So it is zigzag pattern or the jet-shaped pattern. So this is aircraft trajectory here, and we know the coordinate of this trajectory from point to point or even over a fraction of second. And as a result, we can find out what is the coordinate of each and every pulse on the ground surface. So that is the mechanism for the airborne LiDAR data acquisition. So we got this kind of data over the time. As aircraft moves from this point to this point, we got this kind of data in the zigzag pattern of two lines are indicating the swath here. So now aircraft will turn on the next line. So this is the next line here, and so this is the flight line, and this is flight line on the ground surface. Let us acquire the data like this. A scanner is again acquiring the data. Now we can see one more swath. So this is the swath again, and we can see there is an overlap here. So now you can understand what do we mean by overlap and what is the swath. So we are plotting the flight lines on the ground surface or on the map. So we are getting these two flight paths. So the difference between the two flight paths, it's called effective swath or the spacing between the flight lines. We are indicating the flight lines on the map. So this is map here which is showing XY. So we have an area of interest which is written here as AOI and indicated by the black line. There is a closed polygon indicating the AOI. Now we have divided these AOI into the parallel strip. Each strip is called flight strip, and the center line of the flight strip is called the flight path, which is vertical projection of the flight line. In order to acquire the data, aircraft is starting from point S, that is starting point, and it will travel over this line from this point to this point. Then it makes a turn like this, and again from this point to this point it travels in a straight line over the flight strip, and it acquires the data in a zigzag fashion like this. And then it will exit from this point here. Again it will go and come back to this next line, and again it will acquire the data like this in a zigzag pattern. So each line is indicating some data, and it will then exit from this point, and it will repeat the whole process, and finally from point E aircraft will exit. So now we can see that each and every line has some data like this. What about the spacing between the flight lines? This is spacing. It is the effective swath that we have shown in the last slide. So now let us go for the small derivations. What is a swath? This is FOV as 2 alpha, and this is the flying height, and this is the ground surface, which I assume as flat and horizontal for simplicity. So this is the flying height H, and this is swath. Swath is given by 2h tangent of alpha. What is the overlap? If I have two swaths, so let us say this is one swath here. Let us say we have effective swath, and again we are repeating the process. So this is flying height again. So aircraft is moving from this point and coming back onto this point. So this is effective swath, or the spacing between the flight lines. This is overlap from here to here, and this is another swath here to here. So between the two swath we have overlap, and overlap is given by some percentage of the swath. So let us say eta percentage of swath. So I can write here eta times 2h tangent of alpha, and that is overlap. What is the spacing between the lines or effective swath? This is overlap, and now this distance from here to here, this distance from here to here is constant. That means here it is like this, here it is like this, and here it is like this. And so this is the effective swath, or the spacing between the flight lines, and effective swath minus overlap. So I can write here 2h tangent of alpha minus eta times 2h tangent of alpha, or I can also write 2h tangent of alpha into 1 minus eta. Eta, which is overlap, is generally expressed in the percentage. For example, 10%. So it becomes 0.1. So if I put here 0.1, I will get 0.9 times of swath as effective swath. So this is the simple concept of the swath, effective swath, and the spacing between the flight lines. So now you can easily correlate each and everything. So we have learned what scanners are there, like DGPS, GPS, and laser scanner. So what are their characteristics? Then how do they create swath? How do they create laser pulse? And each laser pulse is creating footprint, and it is also creating vertical accuracy. So we have seen all these things in this lecture, in the previous slide, or in the last lecture. Let us look into the user requirements. So what is the user requirement? User requirement consists of two aspects. One is the project requirements, and the second is the mapping requirements. Then we derive resolution of the data, that we'll see later. But before that, we should understand project requirements. So each and every project has some requirement about the data quality as well as data quantity. and these are the project requirements. These are data density, data spacing, overlap, and the errors. We will see one by one all this. But before that, let us look into the mapping requirements. Each and every mapping agency demands some kind of attributes or some kind of quality or some kind of conditions in the data acquisition process, so that data should have some minimum quality. And so data should be uniformly spaced, which means if the data is uniformly spaced, I can create 3D data or the 3D digital elevation model, and we will have more confidence into that. There should be minimum overlap. If I increase the overlap, first of all, I will not get any additional information, because we are getting some information in one side or one swath. Again, there is no point of repeating that information. As a result, we will have minimum overlap. There is one more reason for that. Minimum overlap will increase the distance between the flight lines, and I will acquire the data of a given area in minimum time, because I will have less number of flight lines. That means if the effective swath is more, I will have less number of flight lines, and less number of flight lines means less number of turns, and so overall time of data acquisition in air will be minimum. And that's the reason we prefer the minimum overlap of the data. At the same time, we should understand that overlap cannot be made zero, because overlap is must or it is required in order to maintain the continuity of the data between the two flight strips which are adjacently located. And that's the reason we do not make the overlap equal to 0. We have minimum overlap always. So let us go into each and every term one by one. First of all, we'll go for the data density. Data density is going to tell us that how much data is available in unit area. This is the flight line. We have acquired this data in 1 second. What does it mean? This is the swath across the flight line, and this is the speed of the aircraft. That means aircraft is traveling by so many meters in 1 second. So I can find out what is the area of this data. Area is BS into V. This area is containing so much of LiDAR point data. Now I want to find out what is the quantity of the data per unit area. So I define data density or number of points over unit meter square or unit area as F, that is number of pulses fired in 1 second, and during that 1 second area covered. So this is the data density. The unit of data density is points per meter square. If I zoom in this area, there are two lines of the data here, and it has some data spacing. What does it mean? Data spacing is going to tell how much data is apart from each other. This is the data spacing between these 2 points, which are falling in 2 scan line in one oscillation or one cycle. Moreover, I can say this is the shorter data spacing between this point and this point. So let us call this one along track long spacing, and this spacing is the along track short spacing, because this is the flying direction here. This is the along the flight line, so I am saying along flight line spacing or along spacing. And along spacing, dA, let us say I am writing it L first, this one is given by V by F, where we have the scanning frequency F, because we have one cycle here, then we have second cycle starts here, third cycle, fourth cycle, and fifth cycle. So I have F is equal to 5 Hertz. Now if I divide V by F, I will get this distance as D along track long spacing. Now what about the shorter spacing? The along track short spacing is given by V divided by 2 times of F. So it is up to you which spacing you specify if you want to acquire the LiDAR data by airborne method. Let us define the across track spacing. It is the average spacing between any 2 points here along the swath, and that spacing is the across track spacing. and I am writing it with the help of ds symbol. So ds is given by swath divided by number of points in one line. Or one scan line. So what about the number of points in one scan line? These many points are there. How can I estimate it? We have f number of points in 1 second. So if we divide f by 2f, I will estimate number of points in one line, because there are 2f number of lines and these lines are containing total f number of data. The number of data is this much. So ds is given by bs upon f by 2f, or I can write it 2f bs upon capital F. This is ds, the average spacing in the across-track direction. Now data spacing should be uniform. That means the spacing in the two directions ds and dA, it can be long spacing or short spacing, they should follow some criteria. That means dA minus ds should be within some threshold, let us say delta. Or I can also write dA minus ds divided by dA should be less than equal to some threshold delta t, which is in percentage. Now there is one more requirement, that is LiDAR data errors. There are 4 elements are contributing for the airborne LiDAR data acquisition: 3 scanners, GPS, IMU, scanner, and they are mounted in the aircraft. So aircraft trajectory also has some error. So all these 4 elements are contributing to the error of the data, and as a result we have planimetric error and we have altimetric or vertical error. A user specify the data quality up to so and so limit. Similarly, he has some criteria for the data errors. This is error ellipsoid and this is ellipse of the planimetric error, where sigma p is planimetric error. Now we have altimetric error also. So this is altimetric errors. A user can tolerate error given by sigma p in horizontal and sigma v in vertical. So we should also try to meet these requirements. Finally, I am now summarizing the all project requirements. So first is the error, then we have data density, then we have data spacing, then we have overlap. So let me write the minimum quantities. So minimum quantity of the overlap is 10%. Data spacing, along track spacing and the across track spacing should be uniform. What about the errors? Errors should be generally given by sigma v, let us say some 15 centimeter, and similarly sigma p is given. So these errors which are obtained in the LiDAR data should be less than maximum error. What about the data density? Data density is, for example, a user says I want 5 points per meter square. So this kind of requirements we should be able to satisfy by the airborne data operation. What about the resolution of the data? So far we have talked about the data density, and we are saying that the data density is number of data points over a unit square area. However, if we see carefully, the data density is determined by a large area, that is swath into speed. So that is an average criteria over a large area. Now I want to estimate quality at each point in the data set. I can find out the resolution now, and resolution is the distance between the two data points. If I draw the mechanism again here, the spacing between the points from here to here will be less, like this, for the 2 consecutive or sequentially fired pulses. But if we see here, distance between the 2 data points will be very, very large, and so we define 2 terms. One is the worst case resolution and one is the best resolution. The best resolution we get at the nadir, this, and that is given by Rn h into tangent of delta alpha. The delta alpha is the angle between 2 sequentially fired pulses by the scanner. So if I divide 2 alpha into number of points in one line, I will get delta alpha. So that is the resolution here. Now we can see what is horizontal resolution in the worst case, which is here, RH here. So this is Rn here. So this is RH or R horizontal, and it is given by Rn into sec square alpha, where this complete angle is 2 alpha, or the half angle is alpha, or half of the FOV. So I can write here alpha is FOV by 2. So we have determined that there is a horizontal resolution here for the given delta alpha. This is delta alpha, and so we have higher spacing here. So it is worst case resolution R horizontal. Now for same delta alpha, I have very high resolution over there. So this is Rn at Nadir. Now what about the vertical resolution? So let us say there is a building like this, and then these pulses are fired like this. So you can see here that the vertical resolution is worst at the bottom of a building. So vertical resolution R vertical or RVER is given by Rn times tangent of 90 degree minus alpha minus delta alpha. So it is again the worst or the minimum resolution. So far we have discussed about all the data quality, project requirement, mapping requirement, scanner quality, GPS, IMU and so on. Now we will talk about the flying operations. What are the flying operations? First of all, if you see the first slide, we have drawn some flight strips and aircraft is making the turn. So while making the turn, aircraft, it banks and again it turns back like this in order to reach to the next flight line. So we have some banking angle, and banking angle is limited to 25 degrees to 30 degrees. And what is the reason? The reason is the flying crew should be comfortable, and they are generally comfortable around this value, because this value will ensure that I will take minimum time to fly. At the same time, this turn should be comfortable also. If I increase the banking angle to 45 degrees, it is possible to make the turns, but flying crew will not be comfortable. At the same time, I will have a danger of losing the GPS lock. So we should be careful on that part. So that is the role of banking angle here. Then we have cushion period. When aircraft turns from one flight line to next flight line, it will have some kind of cushion before it starts the data acquisition, that is the starting of the next flight line. And this period we should have to provide to the pilot, and that period is around 30 seconds to 60 seconds, and it depends on the pilot, person to person. In case of helicopter, since helicopter can do the sharp turning, this period reduces to 15 to 30 seconds. And in case of aircraft, it is 30 to 60 seconds. So it depends on pilot which value he prefers. So we have to provide some provision for this kind of cushion also. And that cushion period is very, very important, because during this period only, a pilot ensures that it is going to fly smoothly over the next flight strip after turning. So after turning, he takes this much of time. So then speed of the aircraft should be constant. Now what about the maneuvering? Maneuvering can be done on the consecutive lines, or it can be done with the larger turns. So it will be not on the consecutive flight line, but it will be non-consecutive flight lines. So we have non-consecutive turning and we have consecutive turnings. Well, we are not talking all these things in detail, but I am just giving you some hints here. Then we have minimum height. If I have lower flying height, I can acquire very high data density or high quality of data. But the Director General of Civil Aviation specifies the minimum height, and that minimum height in India is 300 meter as per the DGCA governance. So a pilot has to maintain that minimum height. That means we can not come below 300 meters. So these things has to be taken care when we perform the airborne data operation. Then flight endurance. What's the meaning of flight endurance? According to the fuel capacity of the aircraft. We have certain capacity of flying in air, and in general, whatever aircraft we use, they have some capacity around 4 to 6 hours. Within 6 hours, aircraft has to take off, it has to acquire the data, and again it comes back to the airstrip. So this flight endurance we should always consider when we perform the data acquisition in air. Now coming to the wind, let us assume that an aircraft is heading towards the wind, that is called headwind. And as a result, the speed of the aircraft is lower, and we get higher data density. You can see the expression of the data density. The data density equals to F by BSV. So if I have headwind, the effective speed of the aircraft will be V minus delta wind, and as a result the data density will increase, because if V is there and V is aircraft speed minus wind speed, I will have less effective speed of the aircraft and I will get higher data density. At the same time, assume that there is a tailwind. In case of tailwind, the effective speed of the aircraft will increase. So data density equals to F upon Bs upon V plus delta W. So delta W is wind speed. So I will have inferior quality of data, or data density will be less. So we should consider all these factors when we perform the airborne data acquisition. Now I consider all these factors like sensors, project requirements, field limitations, some user defined preferences like cushion period of pilot or maximum banking angle for the flying crew. Then we have mapping requirements like what is the overlap and what is the data density or nominal pulse spacing. So all these things are contributing to the cost of the data acquisition. So when we integrate all these factors together and we plan the data acquisition exercise by simulation, and this simulation exercise is called flight planning. And flight planning is very, very essential before the data acquisition is really performed in the field, because flight planning only ensures that certain quality of the data will be acquired with certain mapping conditions, with so and so sensors, with so and so aircraft, with so and so characteristics of all the elements involved in the data acquisition. So that is very, very important aspect of the airborne LiDAR data acquisition. Now let us see how to validate whether we get the appropriate data or not. Let us assume after flight planning you went to the field and you acquired the data. But again we know that this is a random sampling of data. Now how to ensure that data distribution is uniform or not? Multiple checks are there, and we are going to learn all these checks in this lecture. First of all, we define a quantity called NPS, nominal pulse spacing. And that is 1 upon root of data density. And I will tell you what's the reason here. The data density is given in points per meter square, that is number of points in unit square area. I want to find out what each point is representing, or how much area is represented by each point of laser data. So if I inverse the data density, I will get the area per point. If I take the root, I will get the size of the area, that is meter per point. That means I'll get some area like this, and I call this dimension NPS. NPS. Each box is having one LiDAR point. So again it is an average criteria, because it is calculated from the another average criteria, data density. So we should understand that how to validate whether data distribution is uniform. Let us say there is one swath here. This is NPS. So now this is the cell of NPS. So we have calculated what is NPS. So now I will take the 90% of the swath. This is the 90% of the swath. I will divide this 90% swath into the boxes of 2 times NPS size. So how many boxes are there? 1, 2, 3, 4, 5. So let us put these boxes in the center 90% swath. Now we'll check that each and every box should have the one LiDAR data point. First of all, we'll take the 90% of the swath, or the center of the swath. Then we'll fit boxes of size 2 times NPS. So these boxes are basically 2 times NPS. this length is also 2 times NPS. So now such boxes are there. Each of the 90% of the such boxes should have the laser data. If it is so, we have the uniformly distributed LiDAR data. So that is the check we always perform. Now, what about the data density validation? There is a area or AOI. So you might be thinking we have already verified the NPS or indirectly we have verified the data density. But there is some debate here. And debate is the data density is again an average criteria. It is used for uniform distribution validation. However, it cannot be used for the data density validation. And so we have a new method now. Let us say these are the LiDAR data points. We will divide these data points into the triangles. And what we call here is triangular irregular network or TIN. I know that each triangle is representing one LiDAR data set, or one LiDAR data point is representing one triangle. But we have different areas of each triangle. What is the consequence here? We have to find some way in order to report the data density. So what do? We take the 95th percentile of the triangular areas. For example, you have total 1000 triangles. You have A1 to A2 and let us say A999 and A1000. So these are the areas of triangles. You will take the order data, that means you are ordered the data, let us say A1 bar, A2 bar, A3 bar, you have ordered this data. So ultimately we have some ordered areas. So higher to lower or lower to higher. You will find out 1 upon A1 bar, 1 upon A2 bar and so on. So each term is now representing data density. They are ordered one. What will you do? You will take the descending order and then you will take the 95th percentile. Let us say this is the ascending order here, ascendingly ordered, so it will become automatically descendingly ordered. Inverse of areas of triangle. Now we will take here 1 upon A bar 950 here, because we want to take 95th percentile. As they are in the descending order, this quantity will indicate the data density. It is the point data density of the airborne LiDAR data, and this is the way we calculate the data density. The other way around is that if I take the F divided by BV, that is an average criteria, but this way I have a point criteria or the point data density. The point criteria is much better than the average criteria over a large area. So now we have validated uniformity of the data as well as data density after the data acquisition. Now after that, I would like to tell you it is very difficult to acquire the LiDAR data because the LiDAR data is very expensive. It involves many expensive resources. First of all, the aircraft, then we have the scanner, GPS, IMU, and the whole logistics of the airborne data acquisition is very complicated, as we have seen in the whole lecture. And as a result, we can see it is not a night game ball or very simple game ball to acquire LiDAR data. It requires a lot of resources, a lot of cost, although the cost will be minimized after we acquire the data for very large area and we use the data for many applications. However, if we have some facilities that can provide synthetic LiDAR data, that will be good enough for me. So Limulator is synthetic LiDAR data generation application, and that is developed by IIT Kanpur by Professor Bharat Lohani, and this is a free software utility. And this is the link. You can download this software utility from this link and you can use it, and you can see that how can you generate the artificial LiDAR data for no cost. You can generate trees, buildings in this software utility, and you fix the parameters of the flight. That means you can fix the speed of the aircraft, scanner characteristics, parameters of this IMU, GPS, everything, and then you can see what kind of synthetic data you get. And then you can understand that how laser data play. So that is the best utility available today. So use the Limulator, try to make some hands-on experience on that. It's very easy. So with this, we understand that how to acquire the airborne LiDAR data. Next, I would like to tell you about the terrestrial laser data acquisition. So we have laser scanner like this on the front face and back face. So now I want to acquire the laser data using terrestrial laser scanner. And let us say I have put laser scanner to acquire data of a railway bridge. So you can assume that train is not passing and you are acquiring the data. You specify the field of view. So that is 3D field of view, and then you acquire the data like that. So this data acquisition animation is shown here. So you sequentially fired pulses, and by this pulses you are acquiring the data of the bridge site. So this is the way the terrestrial laser scanner works. Similarly, now we have the mobile laser scanner. In case of mobile laser scanner, the same laser scanner is mounted on the vehicle like Jeep or car. In that four-wheeler, we have GPS as well as IMU, and as a result, when it moves on the road, it will acquire the data of the buildings, and it is also registering the data at every second or even the fraction of the second. So that is the idea about the mobile laser scanner. So now we have learned that how to acquire the LiDAR data using airborne platforms, terrestrial platforms, and mobile platforms. We also learned what is the quantity of the data, that is data density, and what is the quality of the data, that is the uniform distribution, and other parameters like swath, overlap, and all these quantities. So in this lecture, we have learned what are the attributes of LiDAR data and how to ensure those. In the next lecture, we will learn about the georeferencing or the geolocation process of the acquired data. And we will also learn what are the errors that is available in the LiDAR data. Thank you very much.